Merch.
He's selling
I love
merch. He's
it.
selling merch.
Let's bring in the
Awesome.
next
Great to meet
the
you.
next participant of the Demo Day stream, if we have one.
We got Godela.
Welcome to Demo Day 2025. We are live from Y Combinator in San Francisco.
What's going
Great
on?
to meet you.
Nice to meet you.
I'm John.
meet you.
Nice to
I'm
meet you.
Cinnamon.
Hi, Cinnamon.
I'm Cinnamon. Nice to meet you.
Hi, I'm John.
Abhijit, nice to
Nice to meet
What's
you.
going on?
Can you introduce yourselves?
Yeah, I'm Cinnamon. I'm a mechanical engineer by background.
Cool.
Built hardware for Apple, Google, Slack.
Wow.
Yeah,
Hardware?
Hardware.
Hardware for Slack.
Well,
Yeah.
what do they
Wow.
have at
RF
hardware?
X-Way. The Stanford Linear Accelerator Center.
Oh, that. Oh,
Not
no.
SLAC.
Okay,
Not
okay.
SLACK.
Okay, that makes more
Yeah.
sense. I was
That
like,
makes more
what hardware device did I
Good
miss?
clarify.
Yeah,
Yeah.
Cool. Awesome.
Yeah, so I'm Abhijit. I worked as a researcher at Stanford,
Okay.
a researcher at Harvard. I was like an intern at Intel.
Cool.
Built a lot of stuff, I guess.
Can you pull up on the mic a little bit
Yeah,
more?
absolutely. Yeah.
And then tell us what your company does.
Yeah. So we're Godela. We're building a frontier physics model for mechanical engineers.
Okay.
So currently, AI models can't handle physics accurately
Okay.
because a lot of them are language based.
Yes.
Ours are different. Ours
Okay.
are built to handle physics accurately,
Okay.
which means it can be used as a faster, cheaper replacement to simulations and physical prototypes.
Okay.
This is something that I think a lot of labs like to promise, right? Solving,
Yeah. It was
they like
in
to bring
Sam
up,
Altman's
yeah, they like
blog
to
post
bring up
yesterday.
this idea of solving these problems in physics.
So walk me through. It sounds like you're actually training a model. Is it all reinforcement learning with verifiable rewards, or are you generating a whole bunch of training data? Is there a human data labeling component? Like, what is the pipeline to create what you're creating?
So at a core, we extract embedded physics from data,
Okay.
and that makes it generalizable.
Okay.
Did you want to share more
Yeah,
about that?
so we don't use reinforcement learning or anything. It's basically like this sort of like, encoding framework, like where we actually like take the mesh itself. Like we work with meshes, right? Because we're like
Okay.
in simulation and stuff. So we take the fluid mesh and then we like encode it into like this low dimensional space, and that allows you to like learn the actual physics of the system.
Interesting.
And this allows, and when you do like symbolic regression on like the latent space, you get like a lot of, you get a lot more generalizability than you'd get with like regular models.
Okay.
So, yeah.
when did you guys start working on this? Did you bring it into YC or did you pivot to this at some
We
point?
brought it into YC. So we were TAing a computational mechanics class together at Stanford, which was teaching undergrads in mechanical engineering how to use the traditional simulation software.
Yes.
Kind of bred a hatred for those softwares. Meanwhile, Abhijit's doing insane research at Stanford to use ML to model the physical world in
Yes.
these crazy accurate ways. He's like building ML models for Intel that
Yes.
are replacing months of trial and error in their plasma etch process. And I realized like, hey, there's this huge opportunity to out with these old simulators.
Yep.
Let's bring physics-informed ML to the broader group of engineers who could really benefit from these faster, cheaper answers.
Okay. Try and make it a little bit more concrete for me. I'm familiar with like CFD, computational fluid dynamics. I have an engine and I'm trying to simulate how the air will flow over
Yeah.
the jet that I'm building. Is that an example that we could use to kind of build off of? Is it just faster inference than calculating everything deterministically? Is that the goal?
Absolutely. Like all of simulation, every time you start with a simulation tool, the engineer is starting with a question, right? You've got a question in your
Sure.
3D model. You want to know what is drag
What's the
on my,
drag?
yeah, exactly.
Yeah.
How's that going to change as I change thickness or angle of attack of my
Sure.
airfoil? Now imagine instead of needing to learn a simulation software, you can ask with natural language,
Oh,
drop
okay.
in your CAD,
Cool.
and get simulation quality results instantly.
Interesting.
When we say instantly,
Wow.
it's 4,500 times faster than
Yeah.
a benchmarked GPU accelerated solver that we tested against.
Wow. Okay, very cool. What's the go-to-market like? I mean, I
and
imagine
talk
you're
about
selling to like very large aerospace defense companies, or who else is building stuff? I mean, Apple, Google, these companies could buy this?
Yeah, exactly. I think the huge benefit of physics-informed ML is we can tackle problems that traditional simulators cannot tackle, multi-physics, multi-scale. We make it extremely feasible to tackle those problems, and we can also fill in the gaps where your idealized equations don't suffice to capture the complexity of the problem.
Sure.
So these problems that Apple, Google, maybe aerospace are throwing millions at in terms of R&D and building and testing, we can give you accurate physics models that can replace your need to physically build and test a product. So.
And they can probably like reality check your faster results with the traditional system that they have in place whenever
Build
they
that-
need to,
yeah, and build that confidence in the
run that
product.
overnight
Yeah.
instead of while
Talk
they're live
about
designing.
traction,
Yeah,
selling
how's
it so
it been?
far.
It's been great. So we launched 2 weeks ago. We entered a $25K a year contract with an engineering firm to
Congratulations.
replace Ansys, which is a $30 billion incumbent.
Wow.
However, I think our stronger pull right now is we have some exciting opportunities with enterprise customers to, again, tackle those highest value problems where there is no solution for. For modeling something like drop simulation, right? Like there is no great simulator that gives you that fast, accurate answers, even though it's, governed by
simulation
physics we
software
know.
gets like 70% accuracy or something.
Yeah.
Yeah.
And
Interesting.
it's also very slow though. It's
Yeah,
like 2
exactly.
weeks to compute
Exactly.
a drop simulation on a 14-inch MacBook Pro today. So like these really high value problems for enterprise customers, we have the opportunity to go apply our software and give them more accurate answers.
Very cool. How big is the team? Where are you going next? How's the fundraise going?
Yeah, it's 3 core, 1 advisor. The fundraise is going well. We're
great.
just about, well, it's very exciting. We're just,
Yeah, it's
yeah,
great.
yeah.
Amazing.
You're
It's very busy.
whoever's like, bidding, I'm sure they're, going to watch this. So.
Congratulations on a fantastic demo day. We've been
thank
giving
you.
out hats
Thank
to
you.
folks who come on the stream. Thank you so much.
Thank you so much. Nice to
Thanks
meet
so
you
much.
guys.
Great to meet you
Thank
guys.
you.
Congratulations.